And also, I'd like to thank Dr. Piet for inviting me to this very nice summer school. And I realized that you are very much motivated to discuss a lot of issues. So I'm very much hoping that we can have great discussions during my talk and also after the talk. So the theme of my talk is also about robotics. Actually, I received my PhD from Osaka University, and Professor Minoru Asada is my supervisor for my PhD program, and also now working in his group since 2009. After I got my PhD in 2004, I think so, 2004, I did the 2 years postdoc in National Institute of Information and Communications Technology in Kyoto, and then did my postdoc 3.5 years postdoc in Germany, Bielefeld University, where the researchers also working on the interdisciplinary topics. So today I'm going to talk about our robotics approach to understand the human cognitive development. As Professor Asada introduced, our motivations we want to understand how human infants, human babies, become more intelligent through the interaction with the environment by means of computational approach, which means that developing the robot models. So as an introduction, I also should mention that I briefly changed the title of my talk. I added the social cognitions in the title because the self-awareness is a kind of basis of the social cognition, and we are now developing the many computational models which reproduce the various types of cognitive, the social cognitions in the humans. So my title is Emergence of Self-Awareness and Social Cognitions in Robots Based on Predictive Learning. I will, of course, explain more about the predictive learning in later. So as a self-introduction, I collected some robot video clips which I was involved in the last decades. For example, this one showing my work in NICT in Kyoto. This robot can learn to follow my gaze directions. The joint attention or sharing attention is a very basic social abilities for infants to learn something about the object or languages and so on. This robot first does not have any ability to follow my gaze directions, but then by looking at interesting events or salient events in the scene, the robot gradually learns the correlations between my gaze directions and the object positions, which is acquired as a joint attention abilities. And the top left, top right, you can see the robot which can imitate the robot actions. Of course, you know that the imitation also the very basic abilities for infants to learn new skills from caregivers. In this case, the robot can do a very simple actions like moving the arms up and down or left and right due to just the hardware limitations. But we designed the computational model which can capture the core mechanism of the infant, the imitation, and also the mirror neuron system. And in parallel with the robot studies, I'm also studying the infant development itself in collaboration with cognitive developmental psychologists. This is actually the human parent who is teaching the cup nesting task to his baby at about 10 months old. You can see that he is very enthusiastic to teaching the task. And we analyzed what kind of scenes or what kinds of events are highlighted due to their exaggeration in their actions. We know that the parents tend to teach their actions in an emphasized way. And also we often emphasize the speech. So our question was how this kind of emphasized behavior would facilitate the infant development. And this is the analysis of the infant first-person views. When the babies were interacting with the parents, we again interested in how their infant attentions are guided by their parents' scaffolding behaviors. And so, as a very global motivations, I'd like to remind you about our basic idea that is called cognitive developmental robotics. So as Professor Asada explained, we like to better understand the human cognitive mechanisms by means of computational approach. Especially by taking the computational, the robotics approach, we can bridge the gap between the neuroscience, which is investigating micro level of the human intelligence, and the cognitive science or psychologists, which investigate the behavioral or macro level of the human intelligence. Because our robot systems or the computational models which are embedded in the robots based on the neural mechanisms. And then we can examine how this computational neural model would generate their behaviors, which are often examined in the developmental sciences. But so far, we have developed many types of robotics models. But actually, there is still big differences between the robot models and human development. Here, I picked up some sample studies from our group and corresponding infant behaviors on the right side. For example, the top showing that the robot learns to manipulate an object, as infants do in the very first year of life. And also the robot can imitate the human behaviors. These kinds of behaviors are not embedded at the beginning of the learning, but robot acquires these behaviors, these abilities through the interactions with the human caregivers. But as I said, there is still big gap between the robot actions or robot behaviors and human development. If you look at each level or each behaviors, maybe the robot behaviors looks very similar to the human infant abilities. But then what's the biggest differences between these two? The biggest differences we are facing now is the continuity in the development. The human infants acquire various types of abilities like self-awareness, self-cognition, goal-directed action, object manipulation, imitation, and so on. These abilities are continuous development. Of course, when the development psychologists, for example, analyze the behaviors, they focus on the one specific abilities. But the infant's development is a continuous process. In contrast, robot design, robot development, so far was a kind of discrete stages, discrete phases. For example, my former studies focusing on the joint attention ability only. And then we designed the learning model, neural network model, which enables robots to acquire the joint attention abilities. It was very successful, and it could also capture the core, the most representative behaviors in the joint attentions, which are observed in the human development. But the question is how these abilities are connected to other abilities, imitation, cooperation, and so on. Unfortunately, the previous robotics studies could not answer the questions, what is the continuity, or what produces these continuous processes? And I'm now focusing on to investigate, to verify the hypothesis, in order to, we are very much interested in investigating the core mechanism, the key mechanisms which produce this continuous development. So here the question is, what is the root of the development? Root of the tree, yes?
Sorry, can you just clarify what you mean by continuous there? I haven't got it.
The continuous means that the infants acquire, for example, the self-awareness abilities or self-cognition abilities. And based on this self-cognition abilities, it can develop their object manipulations or imitation and cooperation and so on. So in order to acquire these abilities, the lower level abilities are necessary. That is the continuity.
Are they purely sequential, or some of them are?
Yeah, of course, some can be there in parallel.
Yeah.
Not always something is the only one, the core mechanism. But then at some level, it should have their root, like the seed of the development. That's the point. Not the independent processes.
This also occurred during the Asano-san's talk, but you seem to always put the self-aware, self-cognition at the bottom, right?
It's a kind of trick.
A bit counterintuitive,
Yes.
especially, knowing that, only chimpanzee and dolphin and, all of these high-level animals seems to be able to do it, but, joint attention, imitation, goal-directed action seems to be much easier thing.
Yes, of course, there are some behaviors of the joint attentions can be acquired without the self-awareness or self-consciousness. For example, my PhD studies is about the robot joint attention. And although robot did not have any consciousness about the self, it could acquire the joint attention behaviors. But what is lacking in my model, in my PhD model, is that the robot does not really know that the robot shares the attention with human. Robot can follow the human's gaze as a kind of response to the stimuli, visual stimuli. But robot does not have any idea about sharing attention. That is the biggest problem or biggest difference from the human development. So that's why I put the self-awareness and self-cognition as a very close to the root of the tree. Because without this mechanism, we can design or develop only the superficial joint attention ability, but the not real joint attention abilities, like in infants. Yes?
For the joint attention in the robots, are they specifically trained to observe the same object that they're... Okay, so essentially it's... I mean, I guess the way I would think about it is you can make a video of someone paying attention to the same cup as someone else, and the video doesn't have the ability. It's just a record. So in some sense, it's a record of the training. So how would you generalize that and make it so it's not just a record of the training?
You mean generalize from the joint attention to other abilities?
Well, generalize from the sort of the trained joint attention to spontaneous joint attention, the emergence of joint attention as a mechanism to solve some unrelated stress.
Our model of the joint attentions suppose that the environment is designed for the joint attention. But of course, the robot does not know what's the goal of the learning. The robot just learns the contingency between the sensory signal and the motor output. And then if the outcomes of the motor output is interesting or salient, the robot learns these contingent sequences, sensory motor sequences. The contingency learning is only the core mechanism which produces the joint attention ability.
Okay, so the only thing you're training on is the maximizing the saliency of the things in the visual field, not actually training to mimic the instructor.
No, I mean the goal of the robot learning is to acquire the contingent sensory motor sequences. That's all. I mean, the contingencies are very similar to correlations.
Yeah.
If the robots can find the correlation between the sensory input and the motor output, and also the outcome of the motor output, the robot acquires these patterns using the neural network.
Maybe we should hold the questions until the question period, and we'll have hour to do it.
But I like to receive the questions.
We can also mix it if you feel you are comfortable.
Yeah.
I'm sure you have less than 100 slides.
Yes, I have like 35 slides. Because I want to take more time to explain each slide.
Yeah, you can regulate it yourself.
Yeah, if you have clear, yes.
Yeah, so then, just briefly, then another possible architecture for this is that after learning all these, goal-directed object manipulation, imitation, joint attention, and so on, like modularly, maybe as a result of that, self-awareness sort of emerge. Like, these kind of things, in a sense, you are kind of proving that these things can be done non-consciously, even robots.
Yes.
But to make it sort of integrative and so more meaningful, you might need self-awareness on top of that, right? That's another
I would say it's in parallel.
In parallel,
Actually this morning I was also struggling where I should put self-awareness. Whether I should cover whole things. I don't agree with you putting the self-awareness as a top, but I would say as a kind of covering these whole trees. Because, for example, the goal-directed actions, the robot or the infant can also produce just by accident the goal-directed actions. But in that case, the robot or infants do not have any consciousness about the action and also maybe the self. But it can still produce their goal-directed actions from the third person's view. But then at the end, as in parallel with acquiring a goal-directed action as a conscious process, robot also acquire the self-consciousness. So I would say that, okay, so this is my misreading, but I would say that this self-consciousness or the emergence of self-awareness is a parallel process with all their cognitive processes.
Maybe there are different levels of self-awareness, so
Yes.
yeah, we can discuss about that later in the research
I think
time.
in the following slide, I can answer to your question more clearly. Because this is just a motivational slide, so I will give my answer in the next slide. Okay, so the question is, again, what's the root of the cognitive development? And I'd also added one more slide here. You remember the slide from Asada Sensei's talk? I want to clarify where I'm now attacking in my research. So this is a whole pictures of the human development, starting with the no differentiation between self and others, and then higher cognitive social abilities. And what I'm focusing on in my talk is this process here, the very beginning of the self-other differentiation. First, robot does not have any differentiation between self and others, and then gradually separating between them, which allows the robot and inference to acquire self-awareness and consciousness as well. Okay, then, so this is the outline of my talk. First, I will give you the answer to the questions. What is the root of the cognitive development? And my answer, the keyword of my answer is the predictive learning of sensory motor information. I will give you more detailed ideas in the following slide. And then the second and the third parts, I will give you the more concrete, our studies, the robotics studies, which investigate how the robots can acquire various types of cognitive abilities based on the predictive learning. I will give you two examples, self-other cognition, imitation, and artistic behaviors, how robots can acquire these abilities based on predictive learning. And then in the third part, I would like to extend our theory to better understand the underlying mechanism for autism. Autism is Jihei spectrum show in Japanese. In order to understand their cognitive development, we also have to look at the atypical cognitive development to better understand typical cognitive development. And then we now have a project where myself and the researchers who suffer from autism themselves collaborating and to better understand their mechanisms. So I will extend my theory to understand their ASD as well. So first, what is our theory? Our theory is based on the predictive learning of sensory motor informations. And what is predictive learning? We know that, or neuroscientists suggest that our humans have their body, it's called sensory motor system, and the body produces sensory feedback in response to the motor command and current sensory state. And in parallel with this, our body processes, the human brain has functions to predict the outcomes of this sensory state. And also actually the predictor predicts the motor command in order to execute or collaborate with others. So here is the body sensory motor system produces the sensory feedback, and using the reference copy of the motor command, the current motor command, and the current sensory state, this predictor, in other words, the forward model, learns to predict the future motor command, T+1, and future sensory feedback. And predictive learning is defined as a process to minimize prediction error, which is defined as the difference between the actual sensory feedback and predicted sensory feedback. Here you can take the subtraction from their actual feedback and their predicted ones. And my suggestion is that there are mainly two processes to minimize the prediction error, especially they correspond to the developmental stages. I'm waiting for you to take a picture. Okay, so there are two processes to minimize the prediction error.